Okay, here we go, the final section of higher level bonding. And I think it's fair to say people find this quite conceptually difficult, but actually the IB questions they tend to ask on it are relatively straightforward. So here we go, this is called hybridisation. And you'll be aware, if you do biology, that a hybrid is a mixture of things, and it's the same here. In chemistry, hybridisation is the mixing of orbitals, and that's all you need to know for the definition. Okay, what's the electron configuration of carbon? We're going to look at carbon and how it forms hybrids, and then extend that, or hybrid orbitals, and then extend that to other elements. Obviously, you can work that out yourself, and you can do that bit yourself as well very easily. So looking at that diagram, how many bonds might you expect carbon to form? Two possible answers there. It doesn't really matter which one you get. But when we draw carbon bonding to form methane, we show it with 4 equivalent bonds in a tetrahedral shape. Now if you're thinking about this, you'll think, well actually, and go back to the sigma and pi bonding stuff, you'll think, well, it should form slightly different types of sigma bond, in that, yes, there'll be 2 s overlapping with s, that's 2s orbitals, the 2s orbital, both 2 electrons overlapping with the s from the hydrogens, but then there's going to be some slightly different ones involving the p orbitals with the s orbital of hydrogen, but we show them as all the same, like that. So, what's the solution to this little conundrum? Well, the clue's in the title, obviously. It's to do with this thing called hybridisation. And if we have a look back at the carbon electron configuration, if we provide a little bit of energy to one of the 2 s electrons, it can be promoted into the spare p orbital. Why do you think that might be favourable? If you said it reduces repulsion, then you've got the right answer. So, but the bonds formed would still not be equivalent. You'd have an S there from carbon with the S from hydrogen, but then you'd still have 3 P's with the S from hydrogen. So again, you'd have slightly different bonds. So what actually happens? So here is your definition of hybridisation. It's the mixing of atomic orbitals, if you want, to form new hybrid orbitals. That's all you need. Okay, the question comes up. What is meant by hybridisation? Define hybridisation. That is it. Okay, you don't need to get any more complicated than that. So, there are 3 types of hybrid orbital that we need to know. There's sp3. Oh, sp3. Oh. There's sp2. S, one of those missed out. And there's sp. The S. Oh, and 2 of those missed out. And we'll have a look at each of those in turn. So we will look at each of these in turn. So we get 4 equivalent orbitals. There's the key look, equivalent orbitals called sp3 hybrid orbitals if we combine the 2s and all 3 of those 2p orbitals. There's the sort of thing we get. There are the hybrid orbitals. They're all exactly the same energy you'll see there. And this theory enables us to explain why the 4 bonds in methane, carbon to hydrogen bonds, are identical. Okay, you can read that bit as well as I can. 4 equivalent sigma bonds are formed by overlap with the 4 sp3 hybrid orbitals with the 1 s orbital on each hydrogen. And remember, they repel each other equally, and we get this tetrahedral arrangement that we're familiar with, or should be familiar with by now. So in sp2 hybridization, there is one 2p orbital left over. So these 3 all form sigma bonds, and we get a trigonal planar arrangement, and we've then got one spare p electron. So this is what happens in ethene. The 3 hybrid orbitals form 3 sigma bonds, one to the other carbon in ethene, C2H4, remember. Just draw yourself a quick Lewis structure to remind yourself if you need to. One to the other carbon atom, and one to each of the 2 hydrogen atoms that that particular carbon is bonded to. And then what happens to this other p orbital? Well, that goes on to form a pi bond. Sorry about the horrific picture. With electron density above and below the trigonal planar part. So it goes on to form that pi bond. There are the sigma bonds formed by sp2 hybridization. One there, one there, one there. 120-degree bond angle, like in benzene. Okay, so there we go. It says that the p orbital not involved in the hybridization forms a pi bond between the 2 carbon atoms. So it's just a double bond, remember. That is one bond, and these 2 areas of electron density above and below just count as one pi bond. That is not 2 pi bonds. So in sp hybridization, we end up with 2 spare p orbitals. You can guess perhaps what they might go on to form. But for sp, think about what that shape that might be. We had sp3 tetrahedral, sp2 was trigonal planar, so what might sp be in terms of shape? If you said linear for the shape, by just working backwards, you'd be right. And what happens to those 2 p orbitals not involved in hybridization? Well, they go on to form pi bonds. And the key sort of example here is ethine, C2H2. Again, just draw yourself a quick Lewis structure to remind yourself what it looks like. So we get 2 sp hybrid orbitals, resulting in a linear shape because they repel each other equally. And then we've got the 2 spare unhybridized that form 2 pi bonds. So there's our sp hybrid orbital. Again, sorry about the picture, it's fairly horrible, isn't it? The colours are there. Sp orbital, hybrid orbital, there look. And one there. One bonds with the hydrogen, one bonds with the other carbon. Sp hybrid orbital, sp hybrid orbital. And here's your py and pz orbitals overlapping, yes, I know it's really shockingly drawn, to form the 2 pi bonds. 2 pi bonds, remember, with an area of electron density sort of in there and sticking out towards me. I can't manage to show that very well, and as you can see, neither could this diagram. If you find better diagrams, please let me know. So ignore that, now try the question on Socrative. But there is a key thing here, key idea, that there's a direct link between the number of electron domains and hybridization. If you've got 4 electron domains, whether they're bond pairs or lone pairs, then you've always got sp3 hybridization. And this is the sort of question they'll ask. What type of hybridization would you find in ... 3 electron domains, sp2 hybridization. Easy way to remember it, 1 plus 2 gives you 3 electron domains. 1 plus 3 gives you 4 electron domains. Did I say that in a patronizing enough tone for you? And 1 plus 1 gives you 2 electron domains. So there's a little table on the next slide that I want you to do, and I'll send you a link to a Kahoot as well, but please bear that in mind. Okay, work out the shapes of these and the bond angles, and based on those shapes, what's the type of hybridization? Okay, so have a look through those. There are no tricks. It is as easy as you think it is. So spend some time doing that table. Pause the video, and then when you come back to the video, I will talk through the answers with you very, very quickly. Have you paused it? Why not? So these three are all linear molecules with a bond angle of 180. So the type of hybridization is sp2, 2 electron domains, so sp2. These 3, 4, 5 even, are all trigonal planar. 120-degree bond angle, so sp2. You can follow the pattern. These are all tetrahedral, 109.5, sp3. Now SO2 has 3 electron domains, lone pair, and allegedly a double bond and a single bond, but we know more, delocalized. And this around that centralized carbon there has a trigonal planar shape. So bond angle SO2 about 118 degrees, but in that one it's 120. But the key is the trigonal planar, 3 domains, and so sp2. These are both based on a tetrahedron, but remember there's one lone pair, and that makes the shape, well, I suppose you could say tetrahedral, but it's trigonal pyramidal, bond angle about 107, so 4 pairs, 4 electron domains, so sp3. And water, V-shaped or bent, but again based on a tetrahedron because there are 4 pairs around it, bond angle about 105, so sp3. Okay, so hope you've got that. Shape and type of hybridization. That is absolutely key to what the IB wants you to do. So have a go at the Kahoot as well. You'll need to be quite sharp on that because there's not much time for each question. Let's see who can be the Kahoot king or Kahoot queen.